Thanks for the introduction. Yeah, so my lecture, I learned it as a lecture, so it started as a talk, but I changed it a little bit based on that. So it is about real robot perception for real-life cases and real-life applications. And I would basically focus a little bit on things in the robotic perception domain that we can actually use for solving tasks, also for our customers in the end. Yeah, so let's see, why is it not working? Oh, there we go. So yeah, the outline of my talk is that I give you a little bit of the motivation and the context, then talk a little bit about sensing principles. One important aspect in our work is confidence and error modeling, so that we can basically put modules of software together and always have the reasoning in this separated modules so that we can combine them in different ways. I will tell you a little bit of post-estimation and SLAM. So basically our field is, on the one hand, we have stationary robots, and on the other hand, we have a lot of mobile robot applications. And I'm not sure if the topic was tackled already, but this is also something that is kind of important for us, also for robots, to cover that field. And then I will show you some applications and conclude my presentation afterwards. Yeah, the requirements that we have. So for us, it's always perception manipulation systems that are tightly coupled. So the vision part itself is nice, but in the end, the robot must do something. So for us, it's always the chain from pixel to action, so to say, and we have to consider that already in the design phase of the vision algorithm. So it doesn't help you very much if you are good and working on the image data, but later on you don't get geometry out of it and you need it for your task. So basically, what we are always saying is that you have to see from what is the task, what you want to do with the robot, and so that you consider also the manipulation task in the end. So Markus summarized it very well. Sometimes you have to do placing that has a lot of effect on the grasping. So basically, you cannot really see it separately. You always need to know what you're doing. Same for the human. If I want to drink from a glass, I would never grasp it like this because my task is in the end to do it as such. For the robot, it's even more difficult to represent this kind of information, but that's really the core topic to be used for robots. You have to break down complexity. So in research, most of the cases you have your algorithm, you tune it, it's working well. But if you want to design a system, then it's a little bit what Markus also said is you have a very complex system. You have navigation components, you have detection components, you have something like a controller in there. And you really need to modularize your software to break it down, the complexity, and to elements that you can actually handle and also test separately. We used to have a saying that is the biggest assumable program. That is something you should not do. So basically, think about the structure of your system, design it properly, talk about interfaces in the beginning, not after you did everything, and so you can basically design robust systems. Which brings me to the next point, robust and testability. So whenever you want to deploy a solution, it must be robust because customers expect 99% of performance, and it must be testable. So once you give it to someone and he's using it, and you have no test criteria ahead of time, that's really difficult to do. You also need to be able to adapt your software to a new task or a new problem. And lastly speaking, easy integration into the solution. So what is really a difficult problem that is always underestimated, if you want to do your PhD and you have a real robot, you add 6 months to your PhD at least. Because all the things, if you want to show a real life case that is work, that is never in any of the papers, and it is a skill that you need in order to solve a real life task. Yeah, and in the end, you always have to also see that most of the users of robots are not experts. So they don't know Python, they don't know how to work in a command line, they don't know all these things, they don't interpret error messages. So in order to really apply these to real-life cases, you need to have interfaces that are easy to use, understandable for the people using it. It's, basic example is a car, right? No one needs to know how the motor works when driving a car. So it's a complex system, and you have a very simple input. You have a wheel, you have a clutch, and that's about it. Sometimes you don't even have that, but you're controlling a complex system with a very small interaction design, so to say. For robots, must be the same. If you ever want to bring this to people, to be anyone on the streets to use it, You need to reduce the complexity of the system, but you still need to enable to identify risk. Because on the car, you also know when you're going too fast, that is a risk, okay, you slow down. Same with the robots. What is the risk that comes from a robot, and how do you show that to the person using it? So there's many, many things in that really can enhance or improve the breakthrough of robots in everyday lives, also hinder it. So that's basically something that is in research, not so well covered right now, but for the success of robots, it's elementary to have this in the end. Talking about the market, you all know that the robots are, there's a big expectation on robots. I would phrase it like this. So people are expecting robots to assist them in their life. There will be a big growth in that. You see that robots are getting cheaper and cheaper. That also means that sensors need to be cheaper and cheaper, because you cannot really say if your robot is like, let's say, 10,000 euros, and then you buy a sensor with 20,000 euros, that's somehow not the relation you want to have in the end. So price is a problem there, right? You cannot have the complexity, and you always need, someone needs to earn money with that. So the question is, how do you ensure that you have all this functionality for a reasonable price? If you bring a robot to your home, it will not be 50 or 100,000 euros. No one will ever do this. They need to collaborate with a human, so that's either they share space only or basically collaborate directly, but this is a big challenge here. You're collecting a lot of data. Yeah, if you have a camera on a robot at a person's home, you're recording data maybe all the time. That raises a lot of data exchange and security issues, because basically what happens with all the data? Are you storing that in your system? Easy example, you have a robot at an old person's home. You basically record all the data, and then you ask, okay, give me the tarball of all your data, because I want to check if the system was working. Yeah, you know what you're doing in that moment. Basically, you're taking all the private information you may have recorded, you don't even know. Yeah, maybe there is this relationship that person is not aware of, whatever. You get all this, and then you're looking at and trying to debug your robot, but you're seeing a lot of other things as well. So this is something you have to consider when you're doing all this. Okay, classical industrial vision systems, that's basically not something you can use, because there usually you control the environment. That is something that you, in most cases where robots are applied nowadays, cannot do. Because basically you have to live with the situation that you find on site. So basically you need to guarantee that your algorithm is running independently of the illumination conditions, because you cannot really control it. And for us, we say that most of the things you can only achieve with 3D vision, because the classical 2D vision doesn't give you the scale, doesn't give you the metrics that you need for most applications. So it's always a combination of 2D and 3D in a real application that you want to use. Because otherwise you cannot solve this partial structured, unstructured environment at all, because somehow you need to get that information. Just a testimonial, that's not the newest one, but still shows a little bit what we are doing here. So from the International Federation of Robotics, they say you need to have 3D vision, that's the disruptive technology. Then also Henrik Christian said for the Amazon Pick and challenge, without vision you couldn't basically solve that problem, but that's what you expect from it. Also on the other side, there's expectations, right? So basically, if you say, okay, I have a 3D camera, be it a Kinect or something else, I put it on my robot, the problem is solved. No, that's not the case. There's a lot of things you have to consider in that case. So the expectation is high, and the things you can currently do are still very limited. So most of you have had the experience that you were trying out your algorithm, you were tuning it, and then you're changing it a little bit, the environment or something else, and it didn't work anymore. And this is something, of course, if you deploy a robot to someone else's place, it's not acceptable. Yeah, just an example for 3D perception. I like this video very much because it shows you have tags, you have good environment, and then there's like little deviations, and the whole thing just totally messes up. And you know, that is basically what happens if you do something where you expect everything to be correct, but somehow your model is not. And you detect some inaccuracy in one of the markers, you slightly hit something you don't notice. So that's a perfect example of what can happen if you don't adapt to small changes on the environment, and if you're not considering error in your system. There's a common saying that you say, okay, you can calibrate it, but you can never calibrate the error to 0. So there will always be errors in your system, and the important message is try to treat your error. You know your error, you need to work with it. It will never be 0. You need to live with it. Because if you assume that things are perfect, you're failing anyhow. So basically, know your error and treat it accordingly, because otherwise you will have not any way to solve this. Some lessons here from Nick Corell's paper. So basically he said that, or most of the people were using perception, and also they were considering that as the most important problem there. Then there's the grasping thing, and then you go down to planning, control, mechanism design, and so on. So basically that's, in the robotics, it's never to be forgotten, then control is an issue, but basically the challenges for most people are further up here on grasping, perception, how to basically integrate it all. That's also something that's important because it changed a little bit. The robotics was a lot of the time just more or less control, but not everything you can solve with a control problem. So basically this is what you will have to adapt in future. You can also see that they had a lot of different sensors there. So if you consider that, you have like 3D imaging, Kinect, ASUS, they have just regular cameras, some using laser scanners, distance sensors, also some tactile sensors. They placed it everywhere they could. So basically, the idea was more or less more sensors are good. If you come from industry, the saying is no sensor is a good sensor because it adds complexity. So basically, from research perspective, you like to have as many sensors as possible. From the industry perspective, as little as possible, just basically so that you can have a decent system design and complexity. Yeah, most people were using 3D perception matching to models and so on. It's a nice paper really that sums all the things up that they were doing during that Amazon picking challenge. Most of the teams use structured light. That's also because good depth usually comes at a cost. So if you have a purely passive system, I also introduce it to you. It sometimes has problem when you have non-textured objects and all that stuff. You have holes in your data and so on. OpenCV, PCL was used quite a lot. Most people also are developing own solutions, and this just gives you a quick overview on how this vision approach was in that field. Context matters. We heard this a couple of times before. Basically, if you look at that picture, you see why. So basically, you're assuming a kitchen scene, and you have to look kind of close to see that everything in that scene is wrong. It starts here, so you see this is kind of a Walkman here that is not an oven. Here you would see a chicken, which is actually a nut. You have these little spiders here, which you think are part of the oven. So, and if you look into that picture more and more, you see that basically everything is wrong. On the first glance, you see, okay, that is a kitchen scene. So this is why and this is for the human difficult. So you can assume also that for the robot, that is a big challenge. And I think Markus said it also, the context helps you, right? So if you have context, you can basically avoid disambiguities, you can avoid that things are wrong, unless someone fakes context, as it is done here. So basically, here you're faking a kitchen context, in the end, you're using different elements. And this just should tell you, whenever you have a problem in robotics, check for the context. Ask where it is being used, what kind of things can happen in the scene, what kind of objects can happen. And you also know if then there's an object that's not in that context, you're also getting a problem. So basically, the context helps on the one hand. On the other side, you need to be also careful with context, because if context is wrong, it messes everything up. So this is basically the most important thing, using the context or not. Yeah. This is basically an overview of a perception action loop. Basically, when you want to do something with your robot, you start usually here. You have like a scene registration, you have point clouds, you have black and white, color images. Then you're doing scene interpretation, you're doing plane detection, Markus mentions that, tabletop scenarios, you're clustering your objects. You do recognition, approximation, you do pose estimation, 3D or 6D. That depends a little bit on the application. So that's basically the visual part of it. In many cases, you have context information up here, which is on the object models, because if you have object models, it also contains context, because you're constraining the solution a bit, because you're putting something in here. You have maybe semantic annotations, action restrictions, or what you can do with your objects. You have some mass information. You may also have a graph database if that really helps a bit. But you have to know when you talk about the graph databases, you're also assuming some behavior of your gripper already. So basically, that also couples information here. Then, of course, you have a task information. So what is actually the things you want to be doing? Then you can do, based using all that information, you can do the graph training. You have known objects. You have familiar objects, so that's basically the step where you say, okay, I have to adapt what I know from my known object, and in many cases, you have also unknown objects. So if you're talking about a classical logistics case, usually you have from 2% of all the objects that are coming in front of your camera CAD models, only 2%. But the task is to deal with all of them. So basically, there's a huge problem in between available object data. Also, the worse it is when someone tells you he has a CAD model of something, but it has a wrong scale, it's a wrong thing. Basically, there's a very simple example. If you're talking about everyday goods and you have this Müllermilch, which I've seen also before, sometimes it comes in a 25% more package. But the ID label of that one is the same. So basically, if you have that one in your database and it's different in texture, it's different in size, but the label is the same. So because for most commercial people, it doesn't matter really if the size is bigger or not. Basically for them, it usually becomes at the same price. Or even worse, special edition football world championships, right? If you look at most of the things, then you have a complete different texture on the object still running along the same line. And this is basically there. It doesn't really help to have CAD data or model data because you cannot make sure it's correct. And if you use that, then you're coming into the problem here. Then task information, goal poses, inverse kinematics, reachability is a big issue. So not all the objects you want to grasp you can really reach, or you can access them, or you have some margins left or right of the object to really do this. So you have to do, basically, when you want to commission an order, you say, okay, I have it in my shelf, I want to pick it out, and then the problem is you cannot reach it. So what do? Are you allowed to resort the shelf for doing that? That's sometimes not possible because then you're changing positions there, you have to redo everything again. So that is all the task information that's very important for building in the end an effective solution. It comes to graph sorting, reachability, feasibility, accessibility, then classical thing, your collision-free path planning. Then you go to the execution. And then I think the important thing here is that loop. That is basically the supervisory system. So you grasp something, it shifts a little bit in your gripper, you don't grasp it in the right position, a little bit off, and then you have the task of pack and hold or exact placement. So how do you ever control that in the end? That you're assuming you have the object in your gripper, it's in that orientation. So if you do just pick and drop, no one cares, right? You will always drop it somewhere, that doesn't really matter. But if you want to do assembly in the end, then usually in classical industrial robotics, you go to an intermediate position, you drop the object, you move it against some known geometry, and then you pick it up again. And in this case, you can say that's never be faster than any human, because as a human, you don't need to do this. You check how it is in your hand, you basically insert it, you can correct for all the errors that you have. Now envision that doing a robot, all the small corrections that you do every time, because you're only interested in the relative position in between your eyes, your hand, and the object. It's all relative. Most robots work on a global coordinate frame. So they have a base coordinate system somewhere. And until you go to this relative movement in between this, you have a lot of calibration error and all that stuff that we don't have. We can do this all directly. And this is the important thing here. What happens when you grasp an object? Do you have it correctly in your gripper? Is it in the right orientation? Did you drop it on the way? So there's a lot of things that really need to be done in order to have a performance of a robotic system that allows to be applied to everyday situations. Because, if you get a robot at home and it's dropping your milk every morning, imagine how often you will use it. Yeah? You will say, okay, it's a nice project. This is probably not what I want to do in future. And these things really can also damage, so to say, the introduction of robots to special scenarios. If you do some things too early and you're not really mature technology enough and you show it to people, then they say, okay, go away with your robot. It's not working. Come back in 5 years or never come back at all. And this is also something that I think is very important also for ease. If you bring it to normal people, you should be very careful what you are doing and do the expectation management before. So tell them what you're now doing, what's going to be happen, what's working, what's not working. Because if you lose a large community, then this is not something that's good for all of us developing robot and robotic systems. Yeah, I guess Markus mentioned it also, so we talked about it yesterday, so I don't have to go in depth in that because he explained it all to you already. I just want to give you some famous deep learning quotes. So that's most of the time it's like sometimes it works, sometimes it doesn't. And the second is, which I think is even more difficult, I say I did not need to solve differential equations to solve the problem. So that means that the important knowledge we have is that we try to understand the problem and then we apply something to solve it. If you're using deep learning, most of the cases you're not interested in the structure of the problem anymore. And this basically is totally different to how research was before. And it's also dangerous because you try it out and you see a result and that's it. But you're not considering what is it the kind of problem I'm solving, why is it like this, and so on. Try to find a model or not. So when this was not available, people had to put more brain power into the problem. Now it's more or less you get your data sets, you try it out, it says 99.7. Okay, good. Write a paper, that's it. So we're losing a lot of our, let's say, system knowledge by that. And this is, I think, is dangerous. So we should be sure if you're working with robots, system knowledge, what is really going on is something that must be trained and that you need to keep in your schedule. And same, deep learning techniques require a large amount of data. And in robotics, it's not big data. So in many cases, you don't have the amount of data that you need to sufficiently train. Because you cannot tell anyone, okay, before I can get the first pick, I need to acquire 5 million images of it. So if you go to a customer, tell them that, then they're very nice. How long does it take? Oh, maybe like 2-3 weeks. Then I need to label it, okay. And so that's also something that is really not, beneficial in that sense. Mode of operation limitations, also quite unclear. So what happens if you don't have the right model in your net and you don't notice? Robotics is always about physics. So basically you have some physical relations, there's forces, there's a lot of other things to consider that probably are not correctly represented in your neural network. And in the end, you have a dangerous machine that is moving parts from A to B. And you really need to make sure that it's not throwing the things at the human it's collaborating with. And this is really something where we also should be careful. And lastly speaking, safety, robustness, reliability, dependability in real-life scenarios. So you cannot, as I said, you cannot control the environment. So what happens if a bird flies by, you have never seen this before, it induces some reaction on your system, you don't know what it's doing. That is really something that, for me, basically gives sometimes a bad feeling about many of the learning approaches. So my approach here would always be, if you have a model, use your model, and you can basically start with a mixed approach. So you have a model-based part that gives you some control on the system, and then you have extension for the things you don't have a model of. And then it's kind of clear, you have constrained the problem a bit more, and in the end, you have a working system. So don't learn things that you already have a model for. That will always be bad because it doesn't help. So the key questions, the robot must be enabled to perceive environment, adapt to changes, updating this world model, and to detect changes in plans and plan and perform actions based under these constraints. So basically you want to go from A to B, then there's an obstacle in the way. What do you say? The robot stops and asks for help? No. Of course you have to change the route, you have to change other things. And this is a very tight corridor. You're not allowed to do everything in that case. And this is really something that you need to consider here. So you need to have the representation of knowledge about objects and their purpose. So what can you do with them and how this in the end will work out. You have the representation of context. And you have to work on the representation of uncertainty, because you never know everything. So you just need to bound your uncertainty to a level when you can work with it. And in the end, of course, the supervisory system. You need to also check your actions. What happened? What will be the next steps? How to control it in the end. So basically that's, for real-life applications, that's implicit in all these problems. It's sometimes very simple solutions to that, but it's always in. So if you ever have a robotic system that is running 24/7, your supervisory system may be very simple. In many cases, it is solved by mechanics or something that you cannot do anything wrong. Uncertainty you also can reduce in classical approaches. Also, you just bound the placements of the object, the areas where you can do it. Context is explicitly everywhere. And you know what kind of objects you're dealing with. That means in many applications that you can change the object. You have like 5 kinds of object, then your system is running with these 5 kinds. If you change it to a 6th one, okay, you have to redo everything again. That's, of course, not how we would like to envision that in future, but that is how these questions are solved at the moment in most cases to have robust systems. The most important thing is usually the sensor, because that's the data you are getting. So there's a wide amount of sensors. You can have ultrasound sensors, you have combined laser camera systems, you have panoramic cameras, stereo cameras, you have laser scanners, time-of-flight sensors. So there's a huge amount of sensors you can use. Each of them have a characteristics. So you should also consider what they can measure, what they cannot measure, where are there ambiguities. I didn't show radar here. It's also coming up quite often now because they manage to miniaturize it a lot. But this is basically the base, right? You're getting your data from something that is a physical measurement principle, and this physical measurement principle has errors. It has to be calibrated, and you need to know what kind of data you're getting. If you say, okay, using Kinect, I'm not sure if the same algorithm you were using on Kinect data ever tried out something on some other sensor, because if then it doesn't work, it's probably that you modeled something which is very specific to that one specific sensor without knowing it. I will give you just 2 examples here. One is the time-of-flight camera. So this one is basically an active system. So you're emitting light, so to say, actively, and you have a reference signal, a received signal, and you get basically the amplitude, the intensity, and then in this case it's basically sorting electrons from one to the other. This is the amplitudes you're getting here, and in doing this, basically you can later on determine the distance the object is away. As it is an active system, of course, it's interfered somehow with the ambient light. So you have to make sure that the light you're getting back is really from your active transmitter. There's a couple of ways how you can actually do this, but still sunlight is in many cases a big issue here, especially for that kind of principle. That's also why some of these systems don't work outside. That's the system. Then you have a couple of systematic errors. So you have distance-related errors, you have fixed pattern noise, phase noise, you have amplitude-related errors, and these ones you can tackle by depth calibration. Systematic errors are always nice because that means you can probably have a model for that, you can probably calibrate them. That's the easy part. Then you have other issues, which are flying pixels, ambiguities, regular noise. So what you sometimes have is that you have these flying pixels at shape transitions, so on edges. You also see it in some of your depth cameras. Sometimes the pixel is on the edge, sometimes it's behind the edge, sometimes it's in the middle. That's not a systematic error, so that's not something that you can calibrate somehow. Then you have this unambiguity range. So basically, depending on your base frequency, you have a measurement range, let's say, of 7 meters. And the next 7 meters will produce the same result. So if you're not checking on the amplitude in the end, it can be that the distance measured is 1 meter away or 8 meters away. So that is also an ambiguity that you have to consider. If you do this in your lab, and your lab is always smaller than 7 meters, you never figure it out. But then you go outside to a different environment, to this here, and you have, from one moment to the other, a different behavior of your sensor because you have not considered that it's basically the same measurement, just 7 meters further away. Then it's a difficulty here. So you need to consider that. You have a lot of noise sources, dark current, conversion noise, condensation noise, and that is also something that basically depends on the temperature of the sensor. That depends a little bit on how the special silicium is actually made. And when we started working with that cameras, they didn't have any calibration for it. So that was really hard to use because sometimes it worked very well, and sometimes you just got a point cloud that I would consider is an arbitrary shape in it or whatsoever. So you didn't really know what you were getting from it. Another thing that is also very hard to do is multipath interference. So if you have an active system and you have edges in there, you have reflections and you have multipath, and that is something you can figure only out when you know the environment already, but that is a bit of a chicken-egg problem. If you know the environment, you don't need to measure it. So how do you basically distinguish these areas? You have this, the reflections within objects in a scene, and then you have a received signal that basically doesn't show you the true value. But how do you manage that in the end? And you can see a little bit here the light shattering, which is also interesting for time-of-flight cameras. Things that are outside the field of view of the camera affect what happens inside the camera. So when you're looking at that scene and the field of view ends here and this is black, that has effect on the measurement of the camera. Would it be white? It would be changing. So basically things that you don't see in your image affect what happens in the image. And if you don't know this effect, that's also something that makes it kind of difficult. You need to know about the environment before. That's basically the problem of where to look at, how to do this. So that's really bad. And this is all something by principle that the manufacturer cannot calibrate because the manufacturer gives you a camera that measures steps. But about these environment constraints, you're not really aware of. So basically the errors you have, the flying pixel, multipath, light scattering, the distance-related things, ambiguities, noise. You can solve some of them by calibration. Some of them you can use check out by filtering. But basically the ones that are left, this multipath and the light scattering, that is something without any knowledge on the environment, it's really, really hard to get. If you have the edge thing, you basically just exclude it. You have a filter on that. That's all possible. But multipath and that is really something you will always have in your system. That's a problem with most active systems. The time-of-flight is just an example for that, but it also happens to laser. It also happens to other systems independently. It's just a size issue or scale issue, be it bigger or smaller, if you notice it. The other system I'd like to, or the other measurement principle that we are mostly working on is stereo matching. It's actually a kind of old technology, but still it is a nice one because the good thing is you're working on regular camera images and you're creating depths on that. The main problem why people were not using it for a long time is you had the computing constraints. Basically, you need to do the matching, you want to have then steps mapped, and that requires algorithm with, when a couple of years ago it was not possible to compute it. And the same thing that applied to CNNs, where you say now you have computing resources to do so, is also good for stereo, because now you can have nice algorithms that can be computed on board, and then you can get your depth image. Basically how this works, you have two cameras, the left and the right camera, you have the image plane, and you have here two objects. Basically these two objects are represented in the left and in the right image, and you have a disparity or distance in between these images, this is the representations, when you basically check on the left and right image. And the task is really to figure out how these objects moved from one camera view to the other. It's easy if you do it frontal parallel. That's also what I would mostly recommend, because everything else doesn't really give you a benefit. The other thing that's also a big issue is the perspective constraint. That also helps you when you have it frontal parallel. You have some problems, of course, when things are moving in the image plane or perpendicular to it, but that's still the simplest setting you can do. You have to calibrate the system, so you have intrinsic and extrinsic camera parameters, that is distortion, focal length, height and width of pixels, and this is what you can calibrate easily. And then on the other hand you have the extrinsic stereo camera parameters, where you basically have the distance in between the two cameras. You usually do this calibration by using a checkerboard pattern or some known structure. Most important is always that you're using the pattern in the full field of view of the camera. That's one of the most easy calibration things. What you can do is you have your pattern very small in the camera, you try to calibrate it, you get a good result, but it doesn't apply to the full image, and then that's the most common error here. So it's also for our product, we basically made it safe that the customer cannot do this mistake, because if you're not experienced, you will make it. It's easy, it's detected, it's fine. We always make sure that we are calibrating on full images. The projection of these both images on a common plane, then you have epipolar lines. That is basically when you have a rectified camera image, basically whenever you look for something in the left camera, you find it on the epipolar line on the right camera. That helps a lot to reduce the search for basically the right points. The corresponding points have identical vertical pixel coordinates in left and right image. As you can see, a big problem is, and this is a very nice example, how when things like the stereo are difficult, either you have structures that are along the epipolar lines or repetitive structures that are perpendicular to the epipolar lines, because here you can say it's really hard to say if you're here or here or here or here. So basically that's where these algorithms usually have problems. Repetitive structures that are mostly aligned to either the epipolar line or perpendicular to it. That's also what you need to know, because if you have these scenes, then you don't get, in most cases, you don't get a depth image. So it's just leaving blank. Usually it's not a false measurement, but it's just left blank. Yeah, so then the matching is basically what you do. So you search for the correspondences in left and right images. So that is basically, so if you ever work in stereo, so the Middlebury's pages is basically where you have all the benchmark, all the algorithms, and they also have data sets you can use. So the task is basically very simple, as you can see it here. If you want to find that point in that image in the same line, it's easy. If you want to find that point in the other image here, there's a couple of ways where it can be. And this is a big problem in stereo, no matter which algorithm you use, that you have this ambiguities in the correspondence between left and right. What we are using is semi-global matching. So that's basically very simply explained. So it's a global optimization that works locally. So you have usually global and local methods. Global methods always work on the full image. You can imagine that, of course, comparing images on a global basis to each other is consuming in terms of computing costs. So that's not something you can usually do in a real-time application. And if you have a local thing, which is like a, let's say, a correlation-based stereo, then you have the problem that it's really local, and you have basically the problem that it has a lot of problems with ambiguities and will not produce the best result. It's just an approximation. So global methods always provide the correct result. Local methods are always an explanation. What we did here is basically a combination of global and local. So you can imagine more or less that you have a pixel in the image and you compute through the image the path towards that pixel from 8 directions. And then you have a cost function that you minimize. So basically, instead of comparing that pixel to all pixels in the image, you're taking these 8 paths out of it, and this is something that you can nicely parallelize also on a GPU or FPGA to implement it. That's basically local because it's working on the pixel level, and global because it uses the paths to it. And this is basically the trade-off in between real-time computability and accuracy of a global method. In the end, you usually have a trade-off, and that's the one that we took. The output is a disparity map, and you have this horizontal pixel offsets of the corresponding points between left and right image. And based on that, you have also some problems here when you have like either a missing texture of the scene or occlusions. So when you imagine that you're putting your 2 cameras further away from each other, of course you have a wider range, but that problem will get worse, right? You have different perspectives of both cameras. So it's not like that I say, okay, I want to measure 100 meters, I just take my cameras further away. That will solve the problem. So stereo is also something where you have to consider it's a trade-off between measurement distance and the size of the camera, you would say. So you have to consider that when you design your system as well. And you have to do a trade-off in terms of resolution versus frame rate. So at our side, we can compute it on the sensor. If you go for VGA, it's 3 Hertz. If you go for half VGA, it's 15 Hertz, and it's computed on a GPU. And if you go for a third of VGA, it's 25 Hertz. So whenever you work on that, you have to consider what is actually the frame rate I want with respect to the resolution I can work with. So if you have a very coarse scene, then go to a third of VGA. That's totally sufficient. You also always have to consider that you're getting a lot of points out of that, right? So if you get like VGA in 25 Hertz or something like this, who's ever computing that, right? So you get it, or you can say, okay, I want to have a megapixel camera that produces 25 Hertz. That's something you don't get over a gigabit Ethernet cable. So why do you do this? So of course, if you're a photographer or something like this, you say the more pixels, the better. If you're working in robotics, more pixels don't even solve the problem. So in most cases, you can live with 1 to 2 megapixels, be it a grayscale camera. It solves a lot of problems. You can compute the image. It's bigger pixels, so more light. So that's really something in robotics where you have to check. Yeah, not the high resolution is something for smartphones, and there's marketing for that. But for robotics, you like to go for a nice approach. You say, okay, this is the resolution I need, and this is basically the frame rate I need, and then I can basically apply that. Yeah, how to come from pixel to depth. That's basically the standard conversion here, that you want to get the 3D coordinates in sensor coordinate frame, and you're using the focal length and the disparity value that you're directly computing. And this is also aligned with the stereo baseline, so you can see basically the stereo baseline has a good effect basically on what you can compute in terms of depth in the end if you check on that formula. That is all done by calibration in the end. Coming to the next point, now we have the disparity or depth image. So basically disparity is pixels, depth is range, so to say. They are basically sometimes you're mixing it up, what is what, but in the end it describes the same value. Then you have always errors. They can be introduced by multiple things. You have to always consider a camera as discrete, so you have a pixel size, so to say, that you need to cover. If you have a color camera, it's even worse because you have like 4 pixels that are considering one measurement, so to say, and there's a misalignment in between these pixels. So that's also something that can cause problems. You have mismatches, you have noise. So what I want to show you here is basically that's the regular image. Then you have the disparity image. And what you can compute out of that is an error image and a confidence image. So error image is more or less the 3 sigma range that you're getting. So basically that is always something that you can get from your algorithm in order to basically get an estimate how the error will be. But that doesn't help you anything because it doesn't tell you anything about outliers and that stuff. And what we have here in the confidence image is basically the probability that the true value is within the 3 sigma range. So the error itself, right, it doesn't tell you something about the outliers. If you want to make sure that your robot is always working fine, you should check for more of such a measure as confidence that tells you how much I can rely on something. It's the same if I would talk to any one of you. You're giving me information, and I know you quite well, and I know that you're always telling the truth, then this has high confidence. If I know that from time to time you're not telling the truth, you have 0.5 confidence, and I'm not continuing that story. So basically, that's important, right? That when you want to do automatic processing of data, and also if you want to base decisions on that, you need to know about confidence, and you need to know how to treat the data. And it's not always error, because that is only sometimes the case. The confidence, the error is basically very similar to if you have a stereo system, it's going quadratically up. The further you are away, the error goes up. So basically, the formula is based depending on the baseline. You have the disparity value and the focal length, and then you see here that it's quadratic over the measurement distance, and this can be represented here in the error image. Basically, just based on the distance, you know how your error is. That doesn't say anything about the scene, right? So that's just a statistical measure you have. That's the same for black, for blue, for whatsoever. It doesn't say anything. The next thing is the confidence value. So in that case, the probability is that the true value is at most 3 times the disparity error away from the measured distance. How do we do this? I showed you that SGM is working on this 8 passes. And what we are doing here is basically compare the result of the 8 passes that are computed towards the pixel. So basically, if you say it on a very easy level, the more it differentiates between these 8 passes, the less confident we are in the result. Basically, we are just checking that we have individual measurements in our algorithms that go for the final result. And then you basically see that some of them deviate a lot. And this means that this value is measured probably correctly in distance. You get a distance value, but you don't really trust it in the end. So you can have low confidence and small error. But that doesn't really help you enough. And you can still have high confidence and large error. So this is when you have local texture that is kind of weak. So basically, the probability value or the confidence value is kind of an assumption about what you see in the scene. It has nothing to do with the statistical value that you can compute ahead of time. So basically, you're using a little bit the scene, what you see in the scene, in order to interpret your data, which you always would do. But for stereo, it's nice to do, and especially in that algorithm. For laser, other sensors, it may be more difficult because you somehow have to figure out how to get to such a value. Yeah, then there's for a lot of heuristics you can put on top of that. You can filter your data. You have minimal confidence, maximal depth error, min-max distance. You can do some hole filling. Of course, you're not correcting most of the cases. Sometimes it's really the hole that you're closing in that case. You cannot really make use of that. You can do some segmentation where you have, say, you have a small disparity regions you don't really trust in. That reduces a bit the noise. You can do smoothing on that with median filtering, but it's all steps you put on top. And of course, you can get a nice point cloud in the end, but what you do is that you either lose local texture or you use structure. So you're basically taking something out of the image or the data that you cannot recover if you don't check on the original image. So that's also, it's always nice that you can do all these things, but you're changing a lot as well. Yeah, and you can do something like noise reduction in static scenes where you just say, okay, this is a static camera, I'm just taking 5 images and doing my stereo on top of that. But this means, in that case, no dynamic scenes. So that is also the constraint. So it's nice for some scenes, but you need to be sure what you are doing. Good. How does it look like in the end? So that basically is the whole set of data you get from our system. To the upper left, that's a regular image. Most of the time we are using in grayscale images. But since deep learning is very, very pushy, our color sensors are sold very well because people need color images for deep learning. So in industry, always go for a black and white camera because you have better light sensitivity. Whoever uses for deep learning, they don't care about the camera so much. They want to have color images. Even if the camera is then not as good in low light conditions, they don't care because they need the color. Then we have here the disparity image. Lower left is the error image, and this is basically the confidence image, which shows you that the confidence is pretty high in black and white transitions, which means that's very good for a stereo algorithm. If you have these kind of scenarios, of course, then the confidence is high. So this is basically shows you a little bit of the structure of the scene in the end. Yeah. Dynamic state estimation is my next topic. So now we talked about how to get depths, and the next topic is how to know where the robot is. There's a couple of ways. You can have odometry, wheeled odometry. You can have your kinematics for a stationary robot. But what I would like to introduce here is basically visual inertial navigation. So that is basically using your camera to determine the pose of your system. So the whole story is about what can I do with a camera. I can generate depth images, but I can also measure the pose. In our case, it's a visual odometry, and as we have an IMU, so an integrated inertial measurement unit in our system, it's a fusion from motion from the inertial measurement unit together with a visual odometry. That helps. This combination is kind of helpful because a camera system has a frame rate that is maybe 25 hertz, or visual odometry has like 12 hertz. IMUs are much faster in their measurement range. However, they drift. So a camera drift is usually quite low. So these two together are a good combination in order to make sure that you get a constant pose measurement. This is especially helpful for having like a mobile robot. We started with drones. So we also showed that this can be done for controlling robots, but the basic concept is as such. So what you can see here as an example is we are using a camera system here. It's hand-guided, so someone is carrying it around. And based on the data from the camera, we are extracting visual features. So in that case, we are using a combination of Agast and Brisk. And out of that, we are generating the visual odometry. And this visual odometry is then fused together with an IMU. What you can see here, you can go indoor, outdoor. So in many industrial applications now, it's also interesting for a mobile robot to traverse from one factory hall to the other. And if you have an active system such as time-of-flight laser or something like this, it's sometimes difficult to make this transition. You know, inside the building, it's all fine. But then you have to cross outside through the sun to another hall, and basically the system should be seamlessly navigating through that. This is basically what we can easily demonstrate here. Also, it works if the camera is blinded from time to time, because this will always happen. If you look into the sun, then from one moment to the other, the visual odometry is gone. And if you have a robot, you don't want that the robot is then doing something. So basically, that's why we have this fusion. So it's based on the observed motion of characteristic points, and the assumption is a static scene. So if you basically have a completely moving scene, that doesn't work. So either move the camera or move the scene, but probably don't move both. If you have some slight movement in the scene, it doesn't matter so much. But if I'm like standing in the full image and I'm dancing around, that of course is a problem because all the features move. That is where we have a problem. We have a couple of poses. We can also generate from the different view and see how the observed motions is, and can use that internally right now. It's like at 12 Hertz right now. How does it look like when the system is standing still? You have here your features, and when you move the camera, the features are moving inside the camera view, and based on that you can basically determine how the system is moving. In addition to that, we are talking about the stereo odometry. We have the depths, so that means that we can compute the motion directly. You can do the same with a mono camera, but then you have the problem that you don't have scale. So in that case, you either need some pattern you know, or an initial movement you know, or something like that, in order to estimate the pose correctly. By using a stereo system, all that problem is basically taken out because you know the depths of each feature. The dynamic state estimation incorporates visual odometry, so VO, the IMU, and then it can be also added on with SLAM in the end. So we are estimating the gravity vector, and we are also estimating the camera to IMU transformation. If you check to the left, that's basically the low frame rate, 12 Hertz, and high accuracy for the visual odometry. And we have a high frame rate of 200 Hertz or even more from the IMU, and it's subject to drift. So basically, when you're having an IMU only, it remains stable for maybe a couple of seconds, but after that, basically the pose is just gone. Then we put it to a data fusion, and then we have a dynamic state estimation. So basically what's in here is extended Kalman filter that uses both information in order to determine the pose correctly in the end. The complete motion, basically you have translation and orientation for the pose. We have the linear velocities, angular velocities, accelerations. That's something that we can provide. So if you're interested in that data, you get it. But most people are more or less just interested in the computed pose. And we also have a real-time pose, which is at higher frame rate. So basically, pose is more or less, say, for each camera image, you have a position. If you go for the real-time pose, you have a higher frame rate because that is for you're interested in the alignment in between image and pose. This year, you are interested in just how does the system move, and I don't care so much for the images. You can use the upper part for object modeling, navigation, and the other information if you want to do low-level control of highly dynamic systems, be it a multicopter or something else. Very neat, really high dynamics. So far, most people are using just this. So we don't have a lot of applications here. There's also, the drone market is kind of down right now because you have so many consumer toys there. It's not really something, if you're not a big company, where you really can make money at the moment. Another thing, robotic systems coordinate frames. Just want to mention that briefly. That's also something that most of the times goes wrong. You have always more than one coordinate system. You have a world coordinate system, you have a camera coordinate system, you have your IMU coordinate system, and you need to bring them properly together. Normally, in our case, the current pose is in the left camera, and the IMU coordinate system is where the IMU is placed, and then you have kind of a world frame considered to that. Then you have to do the gravity compensation and the origin so that they're right together, because you always need some initial state when you can start from. That just gives you a little bit of information here on that. It's also when you move it, then basically you have a relative movement of the system, and you're mostly referring the system to the left camera, because if someone in the end wants to use the system, you need to somehow define your system. And also, if you want to calibrate it to a robot, it's very hard to calibrate the IMU to the robot, but it's easy to calibrate the camera to the robot. And this is when you have a reference system in your system with other coordinate systems. It's always good if you take one that you can calibrate also when you put it to another device. The IMU system may be very nice, but it's not really easy to calibrate unless you put it on a robot, do specific movements and so on. It's much more complicated. So this is why we decided, okay, the main frame is in the camera. This is where we relate our internal coordinate systems to, and this is how we also can calibrate it to the external world. It's also just an advice for the real-life case. Be clever in choosing your coordinate system you're working in, because in some cases you can make it easy, in some cases you can make it unmeasurable or something like this. So think of it before, because then it can cause you a lot of trouble if you do this wrongly and you have a system that you cannot ever touch or you don't know where it is and have to get it from CID data or something like this, which are probably not correct. So it's really a big problem here. Yeah, we are doing internally all the transformation, and this is just basically what we are putting out then in the end. To give you an example how this works in practice, so here we are moving the camera around an object. We are using the visual odometry fused with the IMU, and so we can generate a point cloud very easily without any extra reference, be it a robot or something else. That's a nice feature, though it's not really modeling, it's a point cloud generation, so it's not like a mesh or something that comes out in the end, but it shows you a little bit how easy you can generate your point cloud based on that. On top of that, the problem always with visual odometry is you are accumulating error over time. So basically, also if visual odometry you have a drift. Right now we have 1% per travel distance. But this can be also too much in some cases when you're traveling the wrong way, and it's probably the case that you're not hitting the door anymore because your drift just got too big. For that reason, we have an online SLAM on board of our sensor, so you can generate a map during the operation, and here the main purpose of the SLAM is to reduce drift. So it's not the main purpose to create a map, but the main purpose is to reduce the drift of the navigation. So whenever you go back to a place or you recognize a place again, the drift goes to 0. And in this case, you can have really like long-term operation of a system when you're basically recognizing places. It doesn't help you when I'm going from here to Munich. That doesn't work because I'm always going in one direction, so I will not revisit any places. So of course this only helps you if you're in an environment where you're coming back to places you've seen before. So that's also a constraint here, that you say, okay, I have kind of this building and I have a map of that and I will just orient myself back again. Also here, error and confidence help. So to the left, you see the standard octomap, which we used when we generated a map based on that. And to the right, we used error and confidence. So basically what we added is a signed distance function when we integrate the measurements here. And you see that the map in the end is much cleaner because we are just discarding many of the non-confident values. That is not a functionality that's currently in the octomap. So we are currently also thinking of releasing our confidence octomap because it's not something we can really sell. But for these kind of applications, this helps a lot to basically use the confidence. It's a simple change in the standard octomap, but it really gives us much better information here. Of course, it only helps when you have a computed confidence value. If you don't have that, it doesn't help you at all. To show you also a smart video on that, it's taken down in our garage. We are moving here with a turtlebot, so it's not automatically driving or autonomously driving, it's guided by hand. And we generate here a map or a point cloud of the environment, and we are using depth, accuracy, and confidence here as the input data. You see here it's running at a lower resolution, so for SLAM and for building up the octomap, we are not using the VGA resolution because that's really a lot of points. So basically we said, okay, we reduce it to a lower resolution and then we can have it more real time. In the end, you've seen that we also then update the octomap based on the method I just introduced quickly before. Okay, I talked in the beginning about modularity. what you usually have when you go for an application, you have some kind of process model or requirements. So that's basically what should be solved, what is the requirements in terms of picking rate, in terms of, let's say, amount of objects and so on. And on the other side, you have for your application some human-machine interface sometimes. You have the question of intuitive programming, and you also have to consider in that case that the guy that is using your application is usually not a vision guy. So he doesn't have any experience on any of the things I just said before. He wants to use the camera. Like a photo camera or something like this, and he doesn't want to care about focus, he doesn't want to care about focal length or something like this. That's not what he's supposed to do. He gets the camera, is supposed to give him a 3D image, and that's what he gets, and then he works. So basically we are up here, then we are getting our 3D point cloud and also our 2D images. There may be a modeling part of it. Sometimes it's required, most cases not. You may have an object database that contains geometry, texture, also other information about your objects. You may have to do some graph planning based on that. You have a gripper. In our applications, it's maximally, let's say, 3 fingers. Most of the case, it's 2 fingers or suction cups. But that's not like hands or something like this, but it's more or less much simpler grippers and grasping technology. And in the end, you have your object recognition, pose estimation, grasp and path planning. And all these modules, sometimes you have something like this, you have a different camera, sometimes the modeling is done by someone else. So we are not gripper developers, so we have to deal with a lot of different grippers that are coming in place. And this is why you have to design your system on a modular level, that you have nice interfaces in here, so that you can exchange some of the components, and they may work together also with software from others. Most of our assumption is that we require is that each perception module delivers confidence and quality. So that's when something is developed at Roboception, that's a requirement. We always do this, also for object recognition and the other tasks. We are assuming that we have spatially calibrated and timely synchronized image and data. So we have timestamps to everything, and the time is correct. So we are not guessing out of video images where we don't know the timing and all that stuff. So that's our assumption here as well. We can do online recognition and tracking of point clusters and objects. CAD models are sometimes available. That's not always the case. And we are decoupling object recognition from world state. So basically on our side, the object recognition never has a state. So there's only one module that concerns the state, and that is the world model, that basically keeps track of how objects changing over time. Because if you put your world model into your object recognition, it will be very specific. Because then you're basically tackling 2 problems at the same time. That you actually should disconnect, because in most cases you detect objects and you don't care when you see the object next time. In many cases you want to recognize objects, but then you have like an object detection component that has a lot of additional information, such as world modeling, that you don't want to have in it. So that's for me a clear cutting point in between where object detection ends and where world modeling begins. So the one is stateless, the other one has a state. It changes a bit when you talk about tracking, because then you need the state. But this basically assigns then also the tracking more towards the world model, because then you can basically have state only in one. If you have 2 modules that consider state, it's difficult to basically keep track on the correct state in the end. I show you a short object segmentation algorithm. So basically we have 2 kinds of applications. In the one, it's more or less we don't know nothing about the objects or the environments, and in some cases we have information on that. And I will now show you the difference between these 2 cases. On the one side, we have a completely model-free picking of objects. That's most of the time the case in logistics scenarios. You're getting a bin, it's unmixed, so there's always the same kind of objects in, and the task is to get 2 pieces, 1 piece out as quickly as possible. Same as a human does. When a human does it, it can achieve approximately 1,000 picks per hour. you don't have to think about what kind of job this is, but that's basically the performance that's being done there. And if you want to do this with a robot, of course, you have to go to a similar performance. But if you 1,000 picks per hour, you can always, this is really a lot. So the human is very fast in picking from left to right. And sometimes he's not even looking where he's grasping because he can feel and then do it as such. And in order to bring robots into that and to enable that 24/7 operation, that's what you have to do. So what we designed for that is basically a very simple segmentation approach. So you don't go for a two-finger gripper. Two-finger gripper, positioning it, grasping something out, way too slow. The simplest way is have a suction cup, suck it from the top, drop it to the next one. You don't think about placement. It's not really necessary to accurately grasp the piece. Just take it out. The human's the same. If you have it a little bit to the left, just throw it in the bin. That's what you have to do. Our approach here can distinguish between flexible and hard objects. It's segments the scene in planes. You can say some min-max sizes for the segmented faces, and then you place basically a grasp point for the suction gripper. We are using the same approaches here, disparity image, confidence image. We are using that information to segment the 3D point cloud. And to show you, this is one of the few customer examples I can show you. It's actually an Austrian company. They started to go into robotics now, and they are using our cameras for sorting unmixed bins. And what they did is basically they designed a suction cup that can have up to 3 suctions. They have a scale below the bin, because it's also important what happens if you don't grasp it. You need to notice the suction cup knows it, but also you want to know if you grasp like 2 or 3, so they have scales below. That's, you know, for a vision guy, it's really stupid to say, okay, I need an additional scale. But for the 24/7 performance, it's okay to have it. It's not extra cost. But it just helps to make it sure. And what we can do with the camera is basically capture these sports goods. They are all in these plastic foils. You can imagine that it's bad for vision, but still the only task we have to do is basically to find some position on these objects. So you don't care what kind of object this is. If you put another object in, it doesn't matter. It's always going for a suction surface. You can see our cameras are mounted on top of that, and also static cameras help. So if you have your camera on the robot, it's slow. Basically, when it's you have to move, 5 minutes. When you have to move the camera, take the image, move on, that's basically slow. So this is why most of these applications, when it comes to picking time, cameras are external, because you can check on the scene when the robot is moving the part. This really moves it up. And here they are using also the scale below. You can see you can basically pick any kind of object. And this basically was the task. You don't know what's coming, you pick it, and that's about it. They had a picking challenge on a fair where he said the customer is getting something when he can place an object somewhere in the bin and the robot was not capable of picking it. And we were very happy that it didn't happen. So they went it for 3 days. And no one was able to place something in that was not picked. It's not a perfect grasp, right? But it doesn't matter. It's for this task, you just take it out and do this. So that's one of the few examples from customers I can show because they published that video. Object database, I already mentioned that. This is for the case when you have models. And what we put usually in, we have the detection data, we have appearance, we have shape, we have some physical properties. And on the other hand, we have the grasp. And what we do is basically combine the gripper with the object in order to determine the proper grasp on top of this. I will not go too much into detail on that. What we're usually doing, we're teaching one grasp, and then we're extending that over the whole object. So the first grasp is being taught, and then the rest one are generated automatically. To show you how this works, basically to the lower left, you have the world model. There, the right side shows you the camera data. The robot is looking into the bin. It's in this case a mixed scenario. It's picking the object, and you see we are using a grayscale camera, so the point cloud more or less turns colorful when the object is being determined. And then using these kind of object models with a grass on top of it, of course it's here specific to a 2-finger gripper, we can easily empty the bin completely, also independently how the object is inside the bin. It will also go for difficult graphs where you just go to one end of it. Of course, it tries to be in the middle, but sometimes that is not possible, so you can also pick it out. Placement is not considered, so we don't care really how it is grasped. We just drop it, and this makes life easier here. Another use case is shelf picking, replenishing. That's also a very similar use case that you have here in your scenarios. Of course, the problem is that there are tightly packed items. You have the challenge in manipulation. You have a lot of constraints because it's not much space, and you have a large variety of objects. So just show you what we did basically is the pick from the shelf. So we didn't do the replenishment yet because placing of object, and Markus already said that. It's not really research, but it's also difficult. So we didn't do this in the first step because the picking is much easier than the placement. Show you a short video on that. This is what we exhibited also on Hanover Fair. Basically, this one is also, we are having models of all our items. We are using this April tags for large scale items. So you can move the shelf and the shelf position is detected by the April tags we have on top of that. And the robot is doing one scan in the beginning, you haven't seen that, and then basically checking after each of the object is taken out if something else moved in the shelf. In the back you can see the world model, and you can also see that independently on how the object is placed in the shelf, it is able to take it out. The only constraint is there must be enough space left and right of the object, because that's something that's necessary to do this in the end. Okay, oh, that's a music, okay, good. Last example is, maybe I can, there you go. Last example is a combination of multiple tasks. We did this for also a European project here. It's a combination of tech detection, SLAM, and picking items. So we have this turtle bot. It runs with our RC Wizard and the onboard SLAM module. We have a tag detect module, which basically recognizes these April tags and then says which kind of person it is. We generated a map of our office. And then we basically said, okay, we want to pick apples from a supply station and being able to basically place it to the individual persons. So this is basically the map we generated from our offers. And then we have this picking of unknown objects. Here, when we place it to the robot, we have April tags there, so we know where we can place an apple in the end. And so this is independently where the robot is, as long as it is in the range of the robot. There's also, we try to bring all problems to relative movements, right? So that basically we don't have global coordinates, but it's relative between A and B. And this way we can basically then deliver one of these apples to the station and to one of our colleagues. Of course, there he has to pick it out manually, right? So it's not measured which one is empty, but we know how many have been picked out. And as there's April tags below, the robot then sees where there's a free spot. So it's not very complicated, but it's robust and works. So this is how we basically addressed that topic. Okay, configuration calibration is important. So what we did is basically we have web interfaces so that people can use and calibrate our systems. So that's helpful for most customers, and everything can be done in 3 steps. We go for more than one application domain. Right now, a lot of industrial automation logistics, but we also try to move on to agriculture and healthcare, where there's a lot to do for robots, especially in terms of navigation. Conclusion. For us, or for me, the 3D perception is the key for mastering everyday tasks. Don't forget about model-based perception in times of deep learning, so it can solve you a lot of things if you know how the problem is structured. If you use deep learning, basically apply it to problems where models are not available or not computable. So that's basically, for me, the constraint here. Think about consistent confidence and error modeling, which is a baseline for robust perception action loops. And what is a research topic still, and where a lot of effort should go in the future, is this methods for active supervision of tasks. So what's really going on? How do we deal with error in execution of tasks? That's, I think, the next big thing we have to address in robotics. With that, I'm done. Thanks for your attention. Small video is running in the background, but if you have questions, feel free to ask. Thank you very much. Any questions? Yes, please.
Have you ever thought about using more than 2 cameras, maybe 3 or 4 in the system?
Yes, we did. In terms of complexity, we said we wanted to stick to 2. Of course, you can combine 2 or 3 of the 2 cameras, so to say, of the stereo cameras, and you can basically also synchronize them. We also have an application where we're using like 4 cameras for surround view and all that stuff. Yeah, that's something that we are also considering. What is important there, that we synchronize the data over more than 1 camera. And this is in our case done by PTP, so that you have the same time, because each of the cameras has their own computer, so you need to synchronize it. Yeah, especially for mobile applications, we mostly have more than 1 camera. Yeah. Yes.
Could you say a little bit about how you relate the real-world frame of reference, which is your calibration grid, with the robot frame of reference? They're different, and it's the robot frame of reference that you're interested in. How do you do that?
So in most cases, so it depends. If you have an external camera, then usually we place a calibration grid on the robot, on the end-effector, then we move the robot in 4 different positions. There's also a procedure that tells how to show it to the camera, and this is how you get basically the calibration in between camera and robot when it's externally. When it's mounted on the robot, you basically just place one of these calibration grids somewhere in the workspace of the robot and look at from different positions at it. That, of course, has a constraint that either the camera is fixed or the robot is fixed. So if you have both changing, that doesn't work in that case. Yeah. Yes?
Do you use touch sensors for calibration?
No, we don't. We have some test cases where we have some tactile skins on the grippers. We tried that out, but in many cases it was not increasing robustness because of the sensor signal not being clear enough, so to say. So we will do that definitely in future, but right now we don't have a sensor that we can really use for that. Because it's always hard to distinguish between slipping, what kind of, is it grass good or not. Right now we are mostly using just the motor, the motor current to detect the force, and that's it. We don't know if something is slipping. Yeah. More questions? Yes, please.
How much does it cost?
€2,500. Yeah, the base version. And then you can add on more software modules on top. But it comes in an industrial housing, CE certified, so waterproof. Just checking for the outside. Yeah. Yes, please.
I have a question on camera technology.
Yeah.
If you look at it historically, it was developed to kind of capture a scene and give a person an overview of what is around there. But now we're building it for perceptive, egocentric perceptive systems. Would you comment maybe a little bit on what requests you get from your customers, maybe what other camera designs they would want? If you, for example, look at what humans did, and humans in the eye, you have this one very kind of high resolution region, and one region is more for motion. Could you maybe comment on how camera technologies develop?
Yeah. So we basically went to that solution, so this 1.3 megapixel CMOS fixed focus, because we said our task is that within the range of 2 meters, the maximum thing we want to detect is like an area of an Euro palette or something like this. That was the design criteria that's behind that system. If you go for any other camera design where you have, let's say more a fisheye view or something like this, it always comes at the cost of the calibration, and this really makes it problematic in some cases. Also, we have now an opening angle of like 60 degrees. Everything you have beyond 120 degrees is really costly. So all the lens's price goes really up if you have like wide angle cameras. And we wanted to have more or less the same kind of error over the whole field of view. And if you do this differently, it's kind of difficult for the confidence image as well. If you have like high resolution here and lower resolution to the border, so we wanted to make it simple. So for most industrial cases, that is okay. For cases where you want to have a wider field of view, then of course customers are mostly asking for like wide angle views. We are solving it with more than one cameras, as I said. But that's a request, especially for mobile system or robots traveling. You don't see it enough when you have a narrow field of view. And for that cases, this is interesting. We didn't go for panoramic stereo. We checked on that, but we didn't go because we didn't have a use case. So that's something where you go for like surveyors, robots, and so on. But this was not our task here. So there's a lot of demand also for these kind of cameras. But still the calibration and the measurement issue stays, right? If you just have a mobile robot that when you want to position somewhere, that's probably not such a big issue. But if you want to manipulate objects that are around you, then you need more metric information. And this is, again, then a bit of a difficulty there. So I think panoramic images will help a lot. There's also people that are doing stereo computation. I'm really interested what comes out of that. There will be new things coming out. We were not doing it because we were focusing on the algorithmic side. We are not this lens experts, so to say. But I think that's a combination of panoramic and classical pinhole camera. That is, I think, something that makes a lot of sense in robotics. You're welcome.